All right. Thank you for coming. I just want to take a short poll to see how many of you actually use C++ on some. Okay, so that's about maybe 20, 25% of the people here, optimistically. Um, my day job is an algorithms developer. I do a lot of computer vision and machine learning, and C++ has been for the last 20 years maybe the only language that actually gives me the ability to eke out any performance I need from the existing hardware. But at night, my job is I'm a tour guide into the dungeons of C++. Now, C++ is a language that everybody loves, and it's very easy to learn and very user-friendly, as everybody knows, very beginner-friendly. However, it does have a few dark corners, and in fact, it has some very deep dungeons. And today I'm going to take those of you who are brave enough to join me into just a few of the dark corners of the dungeons. This is a very, very cut-down version of a much longer talk, which is in fact a series of multiple talks. And I'd like to take you there. It's so join me, and I hope I think everybody's going to learn something. Some of these things are very scary and very horrifying. Some of them are really cool. And I'm guessing most of you are going to learn something new. All right, so starting at A, we have something called abominable function types. Now, if you're not C++ developers, this might appear even stranger and freakier than you're used to. But if you are, it's probably even worse, because looking at this line of code, I'm not going to point at the screen. I'm just going to describe, because we've got multiple screens here. We have something that looks like a function, a forward declaration, or a function type. However, this function type, this is a very simple function, doesn't return a value, doesn't take any arguments. That's the void, open, close, paren. But it's also decorated with these const volatile reference qualifiers. And we're just giving it a name. I'm calling it using abominable. That's like a type def, giving this function a declaration, a type name. However, there is no such thing as a const volatile reference function. It's a kind of object that doesn't exist in the C++ type system. And the question is, how come this code actually compiles, and where is it actually usable? Because abominable is not a reference type, it's not constant, it's not even volatile in this case. And it's impossible to create a function that fits this interface. And there are some people who are actually actively trying to get rid of this, but apparently it's not that easy. And the reason is that this type of declaration, although it's abominable, is actually a type of forward declaration for methods inside classes. So if I'm trying to be extremely clever, and I hope in none of your teams this is going to pass a code review, let's say I have a very simple rectangle class. And if anyone has ever implemented a rectangle class, they often have these methods called top to get the top, the top coordinate, and the left, bottom, right, width, and height. And all of these have the same signature. They're basically a function that they're methods that don't take any arguments, and they return some, let's say, an integer in this case. So instead of writing out these 6 methods separately, declaring them, I can instead use the abominable function type specifier here. In this case, I call it the int property, which is a function that takes no arguments, returns an int, and can be called even on const qualified objects. And then I just say, OK, I have top, left, bottom, right, width, and height, which have this signature. And of course, at the implementation, they're implemented just as usual. So these are abominable function types. I hope you never actually use this in code, but it's nice to know, and it's a funny, quirky thing. Now, if we move maybe to the most notorious and infamous part of the C++ world, and we had this morning, Patricia gave a talk about security and about undefined behavior in C++. This is a major issue, and most C++ developers love talking about undefined behavior. It's one of the most popular pastimes. And tweeting about it and arguing about it and discussing it in length. And I would say for C++ that most of the UB, we call it UB because we love it so much, most of the UB-related issues originate even before C++. They originate in the C language, and some of them actually have very reasonable reasons why they are in the way they are. But the main problem is that whenever you have an undefined behavior inside your program, it means your whole program is now completely invalid and can do whatever the compiler wishes to do with your program. So it's very easy to add undefined behavior to your program. However, the compiler assumes that undefined behavior never, ever, ever happens. It's like an axiom built into the way compilers are constructed. So whenever a compiler encounters undefined behavior, it is not required to generate an error. Instead, it's going to assume that, okay, maybe this is undefined behavior, but I'm not going to think about it. For me, undefined behavior cannot happen here because this is an axiom. And by assuming this axiom, there are logical implications which make your compiler completely change the logic of your code, sometimes to do the complete opposite of what you're expecting. So undefined behavior is something that can hit everyone and in almost every program. And that's why we have tools like UB Sanitizer, which are specifically made for identifying, locating undefined behavior. And I think back in 1999, I don't know, the slide is cut off a bit, somebody said on Complang STD, I think it was the C language, permissible undefined behavior ranges from ignoring the situation completely with unpredictable results to having demons fly out of your nose. So this is like, if you've ever heard about the nasal demons, this is the nasal demon, the undefined behavior. And I'm going to show you an example. This was very popular on Twitter and Reddit I think last year. Somebody posted this 5-line or 6-line piece of code, which anyone who can read, can understand, even if you're not a C++ programmer. Essentially, the first line, we're just including some library. The second line, we're defining a pointer type, a function pointer type. So we're saying we're giving a name to all functions that return an integer and don't take any arguments. So this is very similar to one of the simplest functions you can think of. In our third line, we're defining a function pointer called do, and this is actually in global scope. And because it's in global scope, this is an object it's a function pointer. And it's not initialized to any actual function, right? So because there is no assignment here. But because it's in global scope, the compiler is generous enough, and it actually has to do this according to the standard. It is initialized to 0. So by the time this object is instantiated, this do pointer is actually initialized to null. The fourth line, we're defining a function called erase all. Now this is a very naughty function, because it's going to essentially erase all of our hard drive. But that's OK, because we're not going to call this function, right? So we can keep on with our program, and nothing happened. And then we define another function called never called. And all it does is it takes this global function pointer do and assigns erase all to this function pointer. So if we ever do call never called, then we're going to be assigning this function into the function pointer. However, we're never going to call it. So up to now, nothing wrong, right? We haven't done anything too scary. We're playing with fire, but we're being careful. And our main is deceptively simple. It just calls do, right? It returns the value of do. Now, remember, the entry point to main, do is in fact uninitialized, or it's initialized to 0. So because we never called erase all, and we never called never called. So in a sense, this is undefined behavior because we are actually trying to call a function through a function pointer that is set to null. This is undefined behavior. And when it's undefined behavior, all bets are off. And the compiler generously generates this code. Okay, even if you don't read assembly, and I must say I'm not a big assembly reader, I prefer other ebooks. What it actually does is erases your drive. Okay, so what is that? 10 minutes. Okay. So this was very popular on Reddit last year because basically this program doesn't do anything, but it does invoke undefined behavior, which got I think it was GCC to generate a program that erases your hard drive, although the function was never explicitly called. So beware of the UB daemon. Right, going on. Continuing to duck typing. Duck typing is an application of the duck test in type safety. So when we're talking about types, it's a popular term of what's called in logic abductive reasoning. And most of you probably heard the term, heard the small quip. If it looks like a duck, swims like a duck, and quacks like a duck, then it's probably a duck. So it's sort of a type by similarity. And this is a very popular type or form of type safety or type structure inside dynamic languages. So things like JavaScript, where once you try to call some kind of method or access a member of an object of some type that you don't necessarily know, the interpreter or the compiler is actually going to check what the runtime type of that object is, and if it does support that method or that object, it's going to work. Otherwise, it's going to crash or generate some kind of error. However, C++ is a strongly typed language, so all of these type checks happen at compile time. However, again, in C++ we've got these nifty things called templates. And templates are statically typed. And that's where duck typing comes into play inside C++, where when we try to instantiate a template with some parameter types, and templates are like generics in some of the managed languages, for those who are not familiar, then at the point of instantiation, when we try to call a method on the parameters type, the compiler is going to warn us. So this is another form of duck typing that happens. It still happens at compile time, but it happens at the point of instantiation. So it doesn't happen when let's say I'm a library writer and working on some kind of a template class. I'm not the one who's going to get the error. Whoever is going to get the error that I'm using the wrong type is the user when they're actually trying to use my template with a particular type that the template is instantiated with. And C++ 20 is probably going to have something called concepts, which allow us to constrain the types that templates will accept and allow to be parameterized on in such a way that that I, as the library writer, can avoid having to let you see all the type errors, and instead you're going to, the error is going to say at the point where you say, okay, I want to instantiate your type, you say, no, this is not the right type. You cannot use it. You cannot instantiate this. Instead of getting some cryptic errors, which C++, cryptic and very long template errors, which C++ is notorious for. So one of the nice, friendly creatures we'll see today are actually flying saucers, or more commonly known as the Spaceship Operator. If you've never seen it before, this is coming to C++ 20. It's a wonderful new operator that we're getting in the language. And what it does is a three-way comparison. So if anyone is familiar with string comparison, which might return a negative number if one string is lexicographically or like dictionary order before the other, it might be 0 when they're equal, and a positive number when it's the other way around. So that's what a three-way comparator does. And the beautiful thing here is that once we define just this single operator, the compiler is going to define all the rest of the comparison operators for us using this operator, and it's going to be optimally generated. So because if we only define, let's say, the less than operator, or less than and equals, then we have to start playing with some logical combinations. But here the compiler is going to do that for us. So, and that's beautiful. So it's just a single line or a single implementation creating all the rest of the operators for us for free. It can give us a consistent interface, and it has a lot more. It has support for partial ordering and things like weaker ordering, like things. If you can think about like low in a case-insensitive comparison, things like that. So it's a very beautiful thing. And just to give you an example of how awesome this is, think about a very, very simple point class. Like this is the most basic point that you can think of. It has two members, x and y of integer. And all we need to do to get all of the comparison features that we might ever want is just write down this line. And it's literally copying this line. The return type is auto. We're creating the spaceship operator. It's taking a second, the right-hand side point. And I just set it to the default. And the compiler is going to automatically not only going to generate the rest of the comparison operator, it's actually going to generate the implementation for this operator as well. And the result is going to be what's called a totally ordered member-wise comparison. So it's going to check all of the members of our class one by one by the order they appear inside the definition. So it's going to check x, and if x is... I have to finish. All right, cool. Yeah, okay. So I have a lot to say about terminators, but she wants me to finish. So I'll just finish with this saying that there are only two kinds of languages. This is Bjarne Strostrup, he said this. There are only two kinds of languages, the ones people complain about and the ones nobody uses. So I hope you enjoyed this. Thank you.